A core driver behind the excitement for NR and NMN has been their association with mitochondrial health. Animal studies show that raising NAD can improve mitochondrial biogenesis, respiratory capacity, and resistance to stress, and some data suggest NR or NMN may boost mitochondrial NAD pools more rapidly than traditional precursors like niacin. But there's a fundamental catch. None of these precursors directly enter mitochondria.
NAD
Itself cannot cross the mitochondrial inner membrane, and mitochondria maintain their own NAD pool largely through intramitochondrial NMN-AT3 activity and indirect exchange via redox shuttles like the malate aspartate and glycerol phosphate cycles. This means all precursors, whether niacin, NR, or NMN, act upstream by raising cytosolic NAD levels, which can indirectly support mitochondrial NAD through metabolic fluxes, but they do not selectively target mitochondria. In fact, emerging research suggests NR and NMN themselves must still rely on cytosolic NAD elevation to affect mitochondria because they are unlikely to cross mitochondrial membranes intact. Thus, mitochondrial NAD restoration depends on systemic and cytosolic NAD pools, regardless of which precursor is used. That said, what if we could increase the local availability of niacin inside mitochondria to drive NAD synthesis right at the organelle? Modern drug delivery science, especially liposomal encapsulation and prodrug technology, provides tools to achieve just that. For example, liposomal niacin, encapsulating niacin in a liposome designed to fuse with mitochondrial or endosomal membranes could enhance niacin's intracellular uptake, bringing it closer to mitochondria. Studies with liposomal NAD intermediates and other small molecules show that this strategy can dramatically improve cellular delivery and bioavailability, and by modifying the liposome surface with mitochondrial targeting peptides, e.g., cytoschiller or TPP moieties, niacin-loaded liposomes could theoretically deliver niacin preferentially to mitochondria-rich compartments. Niacin prodrugs, chemically modifying niacin to create a lipophilic prodrug, e.g., esterifying niacin with mitochondria-targeting cations like triphenylphosphonium, could exploit the mitochondrial membrane potential, which actively draws positively charged lipophilic compounds into the mitochondrial matrix. This approach has already succeeded in delivering antioxidants, e.g., MitoQ, directly to mitochondria, and there is no reason, in principle, why it couldn't be adapted for niacin or niacin analogs to enhance mitochondrial NAD. Biosynthesis. Nanocarrier systems. Beyond liposomes, nanoparticle carriers functionalized with mitochondrial targeting ligands can be used to deliver drugs with remarkable subcellular precision. Such systems are being explored for chemotherapy, neurodegenerative disease therapies, and mitochondrial dysfunction in rare genetic disorders, and could be engineered to encapsulate niacin or its intermediates. These advanced delivery strategies could overcome niacin's classic limitation of poor tissue or organelle specificity, enabling lower doses to achieve therapeutic NAD elevations precisely where mitochondrial dysfunction is most severe, for example, in neurons or cardiomyocytes. Unlike the standard oral niacin tablets, these approaches would bypass first-pass liver metabolism, further reducing systemic side effects like flushing or hepatotoxicity at high doses. Moreover, because niacin's entry into NAD synthesis doesn't depend on the salvage pathway, which relies on NEMPT, often suppressed in aging or metabolic stress, optimized mitochondrial delivery of niacin could offer unique advantages over NR/NMN, which requires cytosolic and NEMPT activity for NAD biosynthesis. In tissues with impaired salvage pathway capacity, a hallmark of many degenerative diseases, niacin could directly feed NAD production via the Price-Handler pathway if it reaches cells effectively. Therefore, while NR and NMN's promise of mitochondrial benefits has rested more on indirect evidence and marketing than direct mitochondrial uptake, niacin's future in mitochondrial targeting could lie in smart delivery systems, liposomes, prodrugs, and nanocarriers that place this inexpensive, proven molecule right at the site of NAD demand. Early research on other mitochondrial-targeted agents demonstrates these methods are feasible, safe, and effective. In essence, there is no biological barrier preventing niacin from being optimized for mitochondrial NAD restoration. Rather, the missing ingredient is innovation in formulation. Such advances could allow niacin not only to match NR and NMN's theoretical mitochondrial support but also to do so at a fraction of the cost, with the added benefit of niacin's unique GPR109A mediated anti-inflammatory actions.